So for day 110, we start with what's called the Euler identity, and this is one of the most famous statements in all of mathematics. Turns out that e to the pi I equals -1, and this shows up in Germany, spray painted along a wall someplace. That's how famous it is. If I bring the -1 to the other side, we wind up with e to the pi I plus 1 equals 0, and now 5 of the most important objects in mathematics are contained all in a single statement. 0 and 1 are the two most basic numbers. E and pi are the two transcendental terms, transcendental constants, and I obviously is the square root of -1. So it's kind of interesting that 5 of these statements show up in this identity, and we'll be proving why this identity works towards the end of this lesson. So this first slide looks awfully busy, but all it is a review of stuff you already know. We've taken Taylor approximations for polynomials and discovered that the function value at a certain c plus the first derivative times x minus c plus the second derivative divided by 2 factorial models certain functions, and this can be compacted into series form to look like this. If you're going to be centered around 0, then x minus c just becomes x, and you wind up with the Maclaurin series that we looked at like this. The expansion is here, and in compact form, it's like this. So the series version of a Maclaurin polynomial is written like this. So let's come up with the Maclaurin series for f of x equals sine x, and we're going to, because it's Maclaurin, we're going to let c equal 0. So we start as we always do, find the function at c, you get 0, find the first derivative at c equals 0, you get 1, etc., etc. So I build my table of values. I build my Maclaurin expansion, 0 plus 0, x squared over 2 factorial. So all I'm doing is taking these coefficients and putting them in the expansion, simplifying, and then now to put it in a compact form, I'm going to start counting at 0, n equals 0, n equals 1, n equals 2. The pattern is the exponent is odd all the time, so it's going to be 2n plus 1. The denominator is odd numbers raised to factorial, so 2n plus 1 factorial, and it's alternating back and forth between +1 and -1, so it's -1 raised to the, whoops, I'm missing my exponent, -1 raised to the n. When I plug in 0, I get +1. When I plug in 1, I get -1, etc., etc. So now we have the Maclaurin series formula for sine. So there's a page in your book that summarizes some of the most famous power series for elementary functions. We just proved this one here, the sine one. You're responsible for remembering two others. E to the x we did earlier in this chapter, and then cosine is similar to sine, except the exponents are even, and instead of starting at 0, it starts at 1. So you'll have these memorized. I don't know that you necessarily need to memorize the formulas at the end, because they should jump out of the page at you if you look at the patterns that are being formed here. So now we're going to use these three memorized series to expand into other functions as well. First example, now we're going to create a power series for x squared sine 2x. Well, we found sine x earlier, and this has the odd powers alternating between +1 and -1 with denominators that are also odd. So to get sine 2x, I'm just going to replace all my x's with 2x. So first x becomes 2x, x cubed becomes 2x quantity cubed, etc., etc. And now I'm going to apply my exponent, but I'm not going to multiply this out, and you'll see why in a second. So now I have 2x, 2 to the third, x to the third, 2 to the fifth, x to the fifth, 2 to the seventh, x to the seventh. And when I take the next step, which is multiplying by x squared, the exponent now for x is going to increase by 2. So what was x to the first becomes x to the third, what was x to the third becomes x to the fifth, etc., etc. Now that I have my expansion, my Maclaurin expansion for x squared sine 2x, I want to compact it and figure out a closed form or a series representation. So again, I'm going to put my labels 0, 1, 2, 3. And if you look towards the end, I have odd, odd, odd. And the difference is that the exponent for the x is 2 larger than the other two odds. So if I start these two odd numbers as 2n plus 1, then the increase of 2 for the exponent becomes 2n plus 3. And if you check 3 plugged into these two formulas, 2 times 3 plus 1 is 7, 2 times 3 plus 3 is 9, and 2 times 3 plus 1 is 7. So 2n plus 1 and 2n plus 3 work. And now when I go look at my signs, positive, negative, positive, negative, I'm going to take -1 and raise it to the n power. There, we have a series representation for the function x squared sine 2x. Okay? Second example, for sine squared, you're going to use the trig identity that we used earlier, 1 minus cosine 2x over 2. And now, if I take both terms and divide by 2, I get that statement. And now I'm going to use our cosine expansion from the previous slide, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, et cetera, for cosine. So I'm going to take 1/2 minus 1/2, and cosine, what was x is going to be replaced with 2x. So x squared becomes 2 squared x squared. X to the 4th becomes 2 to the 4th x to the 4th. X to the 6th becomes 2 to the 6th x to the 6th. And the denominator stays the same. Distributing my negative 1/2. The first two terms are going to cancel out. And now I've got 2x squared over 2 factorial minus 2 to the 3rd x to the 4th over 4 factorial. Again, don't multiply these out and reduce them. Try and figure out what the pattern is, so that you can figure out the smaller compact version that's the series. So again, alternating series, positive, negative, negative 1 to the n. If I look at the exponents for the 2 to the 1st, 2 to the 3rd, 2 to the 5th, that's a series of odd numbers. So 2 is going to have an exponent of 2n plus 1. But the x's and the denominators are even numbers. X squared, x to the 4th, x to the 6th. So that's going to become 2n plus 2. Again, if you plug in 0, 1, 2, you'll get these first three terms, and you can verify that this is the series representation for f of x equals sine squared x. So last example of the chapter is proving that e to the pi I equals negative 1. So we're going to start with e to the x and write out its expansion, 1 plus x squared over 2 factorial, et cetera. Replace the x with I theta. So everywhere there's an x gets an I theta, all the way down. Now we're going to separate this into two groups. The green lines will eventually combine to be cosine theta. So I have 1, I squared is negative 1, so minus theta squared over 2 factorial. I to the 4th is positive 1, so that's theta to the 4th over 4 factorial. And this pattern is cosine theta. If I take the other ones, I remains, so I have I theta. I cubed is negative I, so I have negative I theta cubed over 3 theta. Over 3 factorial. I to the 5th over 5 factorial. That's the same thing as saying I times sine theta. So that means that e to the I theta is the same thing as cosine theta plus I sine theta. Well, now if I change my theta into a pi, or substitute a value in for that angle, pi, I have cosine pi plus I sine pi. E to the pi I, the value of each of these, negative 1 and 0. E to the pi I equals negative 1, or e to the pi I plus 1 equals 0.